All right, everyone, if everyone could get settled, we'll have our final talk of the day. We are lucky to have Professor Jeffrey Fessler here, who's at University of Michigan. He received his BS in electrical engineering from Purdue University, an MS in statistics, and MS and PhD in electrical engineering from Stanford University. He's the William L. Root Collegiate Professor of Electrical Engineering and Computer Science at University of Michigan, and is also affiliated with the Biomedical Engineering Department and the Division of Nuclear Medicine within the Department of Radiology. His research interests include medical imaging, tomography, non-parametric estimation, and inverse problems, with current and past projects in X-ray, CT, MRI, PET, SPECT, radiation therapy, and image registration. He's a recipient of the Francois Herbsman Award, the Edward Hoffman Medical Imaging Scientist Award, and the IEEE EMBS Technical Achievement Award.
Thank you very much. And thank you for inviting me to participate in this this day. This talk will be mostly tutorial, probably about 2/3 of it. So some of you will know this probably better than I do. And then the last part, if time permits, the last third maybe will be a little bit newer stuff that's very much work in progress. And that last part was really the results in the last part were all generated by my PhD student, Jason Hu. All right, that's what I just said. So you don't have to come to a symposium like this to know that generative models are hot. All you have to do is pick up the New York Times. There's been a whole bunch of articles in the popular press about generative models recently. This is one just taken from a couple months ago, an opinion piece written by a movie director about a hypothetical movie that they showed these stills from. A hypothetical movie that might have been the vision of the Chilean director Alejandro Jodorowsky if he had written produced a version of Tron back in 1976. And Frank Pavich, who wrote this opinion piece, said he wants to see this movie, but it doesn't exist. These are just computer-generated stills from that movie. And he went on to say in the article, if this had been a real movie, I would be nominating the costume designer for an Academy Award for costume design. So this is just an example of generative models in the popular press. Here's some more articles from the New York Times talking about generative models making faces with various characteristics, about some other things you can do with generative models, including even sort of synthesizing new proteins. I work on the field of inverse problems, how you take the raw data out of an MRI or CT scanner, which the raw data is not interpretable by a human. It has to be put through sophisticated processing algorithms to turn it into images. And in that field, generative models have really taken over recently. And there's already a survey paper from a couple months ago surveying generative models in this context. And they go through a whole variety of different models, including GAN models, autoencoders, normalizing flows, and then a whole lot of focus on diffusion models, or score-based models, which is what I'm going to focus on in this tutorial today, because it's perhaps the latest and hottest version of generative models. In fact, there's a website you can go to. The slides have links in them, by the way, that has a GitHub catalog of all sorts of papers on generative models, especially the diffusion kind, including already 5 survey papers on this topic. And so this is AI and science and engineering here. So let me put this in context of what I do, say with a little pictures, what I said a second ago. So if you go have a CT scan, which hopefully you won't need to, but if you do, your body has some density in it, you shine X-rays through it, and you collect measurements. The scanner collects measurements called sinogram that I can actually show you as a 2-dimensional array, but it's not a picture that a doctor could look at and make a diagnosis from. It has to go through this reconstruction algorithm to produce pictures like the one shown on the bottom that are reconstructed by different methods. And this is papers taken from Song et al. From iClear 2022, where they are specifically working on what we call sparse view CT. So a normal CT cytogram, you take an X-ray source and you rotate around the patient, you collect 1,000 pictures, and from those 1,000 pictures, you reconstruct the 3-dimensional distribution of the patient. If you only collected 100 pictures, or in this case, only 23 pictures, then you wouldn't have to have the X-ray source on as much, and you could reduce the X-ray dose to the patient, but you'd have a lot less data. I hope you can see this size of array here is much smaller than this size. And so now you got to work with this little array and reconstruct the same 3-dimensional volume. We're showing one slice of the 3-dimensional volume here. And so that's a much harder problem. It's a very underdetermined problem. And when the problem's severely underdetermined like that, you need prior information in order to make up for the missing data. And this is where generative models can have a role. I might show these pictures again later, but this is several different recent methods for reconstructing from such sparse view with limited data. And the method that works the best is one that's based on a score-based diffusion model. And I've looked at a lot of pictures like this. It might not be so easy to see from the back of the room, but these are really quite impressive results, both visually and in terms of the signal to noise ratios, like this PSNR 35 versus all the other methods that are 32 and below. That's a significant improvement in signal to noise ratio. Okay, so that's sort of the motivating introduction. So now let me dig into a little bit the tutorial aspect of generative models. So what is a generative model? It's a model for some probability distribution, and typically a method for drawing samples from that distribution. That's the generative part. And when you think of generative, I think of a random number generator. It's a thing that generates random variables from some distribution. Keep in mind the distributions that I'm aiming for here are distributions of pictures like this. So this is a probably 512 by 512 image. All right, so it's that vector X there in 2D is already like a lot of variables. Okay, very high dimensional space. And usually we model these distributions in a way that depends on some sort of parameters. So we work with parametric models, right? You're all familiar with the bell curve that has a mean and a variance. That's two parameters. The distributions for time-bound imaging have billions of parameters, millions or billions of parameters. And so typically the first challenge in working with generative models is learning those parameters from training data. You hope that that training data is representative so that when you use that model for subsequent inference or other tasks, it will be representative. And there's lots of concern about having incomplete training data, insufficient variety of skin color. In the medical business, we worry about not having enough examples of abnormalities such as brain lesions and so on. So that's the first challenge, is training these models. And then the second challenge is actually drawing samples efficiently from those distributions. I'm going to talk about both. So just to really make things simple, I'll start with a very simple example. Here's some training data. So it's, I think, 100 numbers. And instead of just showing you the list of 100 numbers, I'm plotting as a histogram, which is already kind of suggestive of a probability distribution. And this happens to be a gamma distribution, and I could fit by maximum likelihood method the two parameters of this gamma distribution. It turns out, if you look this up on Wikipedia, even that, fitting those two parameters to this one-dimensional distribution is not trivial. It requires an iterative algorithm involving an acceptance rejection method. This is not one that you can solve in closed form, as far as I know. Okay, so that's the what of generative models, and then the why. So the obvious reason you'd want generative models is to generate things, right? Generate samples. And the examples I've already given you from the New York Times are sort of about generating pretty pictures for graphics, and you might want to generate jazz music or poetry or whatever. When we do that, often we want conditional generation, right? We want to draw samples from a distribution conditioned on some variables, like we might say, generate a jazz melody, not just an arbitrary jazz melody, a jazz melody in the style of Miles Davis, right? So you'd be generating jazz melodies conditioned on given some particular style, for example. So in the spirit of that, I asked ChatGPT to write a short joke about AI, right? So ChatGPT, I think, is a generative model. And so it should be able to generate things in response to prompts. So it's going to draw an X from some distribution that has buried in its code. Given the input, write a short joke about AI. And here's what it came up with. 3 really bad jokes about why did the AI cross the road. These are so bad and so similar that I thought I better check to make sure ChatGPT is actually a generative model. So I asked ChatGPT, is it based on a generative model? And the answer is yes, it's based on a generative language model. Specifically, it's built on the generative pre-trained transformer. So the G in ChatGPT is generative. So I don't know why it's so bad at making jokes about AI, but there is some randomness to it, right? It didn't generate the same joke 3 times, just very darn similar jokes 3 times. All right, so that's the sampling part. That is not my interest in science and engineering necessarily. That seems more entertainment focused for generative models. I'm interested in generative models for Bayesian inference. All right, so I'm given some test data, a CT sinogram, for example, in my medical imaging problem. And I know the CT scanner is built by a human, so I know how it works. So I know if patient X was in there, a patient with density distribution X in there, I could predict what the measurements should look like according to the physics and statistics of that scanner. And so that's a likelihood function that I can write down. And I want to solve the inverse problem. I'm given the data that comes out of the scanner. I'm given Y. I want to solve for X, the distribution of density inside the patient. And there I'm using the term density as in mass density, not probability density. Sorry, there's two densities floating around here. And if it's a sparse view CT problem, that's an underdetermined problem. So if I simply try to do maximum likelihood estimation, which is a classical statistical technique, of course, for estimating, for doing inference, that won't work well because we have more unknowns than knowns in a sparse view CT problem and in a lot of inverse problems and estimation problems. I also work on MRI where we try to make the scan shorter by collecting fewer samples. And when we do that, the number of pixels in the image we can reconstruct is more than the number of case-based samples we collect. So again, it's an underdetermined inverse problem. So we need some method of resolving or dealing with that underdeterminedness. And one way to do that is to have a prior and then use the posterior as our method of estimation. So the Bayes rule tells us the posterior can be written in terms of the likelihood and the prior. And so everything here, the generative models really is about sort of defining those priors. All right. And so here I would say the purpose of the prior is more about quantifying probability than about generating models. I want to be able to say this type of brain image is more likely than this type of brain image. So if I look at all of the images that are consistent with the data, in an underdetermined problem, there will be many images that are consistent with the data. Of those, I would like to choose images that are more likely according to my prior. So that's what P of X is doing in that Bayesian inference setting. All right, so this is still undergraduate level statistics. And once we know how to define the posterior, means, again, the likelihood we usually know from physics, for human-made instruments anyway, it's the distribution of the things we're studying that is harder to get at. But once we can get at the posterior, we can do many things. We can do maximum a priori steer or map estimation, where we find the most likely image from a posterior point of view, or we could compute the conditional mean, which is kind of a nasty integral, but remember we're in millions dimension parameter space here, but that is the minimum mean squared estimator. Or we can sample from the posterior, which is useful for quantifying uncertainty in inference problems. So in every one of these problems, we need the prior. All right, so that's what's focused on generating generative models. Well, I said we need the prior, but we actually don't need the prior. All we really need is its gradient. And here we need to divert between what machine learning people call the score function and what statisticians call the score function. So Fisher et al., they called the score function the gradient of this log prior, or gradient of respect to the prior with respect to the parameters theta. That's not what the machine learning community is calling it, or the computer vision community. Throughout this talk, the score function will be the gradient with respect to the latent parameters x that we're trying to estimate. So that's, I didn't invent it. That's just where the field is. You have to depend on the context to determine what score function means. So throughout this talk, it'll mean the gradient with respect to x. Because if you have the score function, that is enough to draw samples from that distribution using what's called Langevin dynamics, which you can also just think of as stochastic gradient descent of the log likelihood. So you start with some initial guess, could even be 0 or some random numbers, a random vector here, and then you start adding to it the gradient of the score function, the score function, which is the gradient of the log prior, plus some perturbation that comes from the normal distribution with the right choices of step sizes and noise levels. And when you do that, you can mathematically, under suitable conditions, prove that you can generate samples from that, from the distribution described by P of X semicolon theta. So what we really need to do here is not learn the prior, we need to learn the score function, which is the gradient of the log prior. And by the way, I have plenty of time, so I'm happy to take questions along the way. This is supposed to be tutorial at this point anyway, so feel free to interrupt any questions at any point. Yeah.
It sounds really similar to like an MCMC.
That's right, exactly. And I won't be, the question is, this sounds very similar to Markov chain Monte Carlo, and I'm not enough an expert on those techniques to tell you what is the difference between them. I think this computation is perhaps simpler than what's involved in Monte Carlo, MCMC, but I agree that looks like a lot of similarities here. In both cases, you're trying to sample from a distribution. So the high level, they're absolutely doing the same thing. They're drawing samples from a distribution that's too complicated to just call rand-n or whatever in your computing language, right? The mechanics of what's going on underneath, though, I think is quite different. Other questions? Okay. So the typical distributions that we deal with, at least in imaging problems, have this sort of exponential-like form where we say there's the probability is e to some function u, then in imaging we also call it energy function, borrowing terms from physics. And then there's a constant out in front that's designed to make sure that this distribution integrates to 1, like any probability distribution must have. And if you try to use that form to do maximum likelihood estimation, you'll immediately have challenges because, okay, so you say, all right, let's suppose I'm giving some training data that's independently identically distributed. Then I need to maximize over the parameters of the distribution, the joint probability of all my training data. And you can rewrite that as in terms of this maximization problem. And the annoying thing about this maximization problem, it depends on this thing called the partition function, this normalizing constant. It's a constant with respect to x, but it's not a constant with respect to theta, and typically it's intractable. For interesting probability distributions, we usually don't have a closed form or an easy way to compute z of theta. And so this is why we want alternatives to maximum likelihood for learning parameters of statistical distributions. Whereas if you work with the score function, this turns out to be easier because the score function, if you take a probability distribution of this form, very common form in modeling distributions, you take the derivative with respect to the x of the log of that. Thankfully, when we take the derivative with respect to x, the annoying partition coefficient goes away, and you're left with just the gradient of the part that you've probably mathematically chosen how you want to model this energy function. So this is part of the reason score functions are so popular in the last decade or so, is because of avoiding dealing with this partition coefficient. All right, let me try to give a little more graphical insight into what score functions look like, starting with the simplest distribution of all, maybe the Gaussian distribution or normal distribution. So there's a plotted distribution. If you take the log of that and take the derivative of it, you get a straight line. In fact, there's the derivation, the formula on the below. It has an intercept with 0 at the mean, and it has a slope that's inversely proportional to the variance of the distribution. So if we're modeling Gaussians, this would be a pretty easy thing to do. Something like the gamma distribution that I mentioned earlier has a little more complicated score function. But what you'll notice is to the left of the mode, the mode here happens to be 7 for distribution. To the left of the mode, the distribution is, the score function is positive, and to the right of the mode, it's negative, because the score function is the derivative of the log of this. And so that means the score function in general is telling you which way to move towards the mode or modes of the distribution, right? So if you're to the left of the mode, the score function is positive, saying, hey, if you want to go uphill, go to the right. And if you're on this side, it's telling you to go left, okay, because the score function is negative. That's the intuition in 1D. Here's a more complicated example. This is a one-dimensional Gaussian mixture model, has multiple modes, and now the score function goes through 0 multiple times. And at every point, the score function, the sign of it, is telling you which direction to go uphill towards one of the modes. So when we model distributions by modeling the score function, we're somehow parametrically, fitting these things, not these things. Okay, if this was a class, I would have an interactive question at this point. You get out your clickers, and I would say, can you recover the PDF from its score function in a one-dimensional example like this? So no clickers, but anybody want to answer? Can you, if I give you the score function of a distribution, can you recover in 1D? Can you recover the distribution? You're not supposed to ask questions in a seminar, right? All right, so anybody? AI, I should call on one of the AI fellows, but I won't do that. So, okay, so it's just the derivative, so you can integrate this, right? And then exponentiate, but then whenever you integrate, the antiderivative, there's an extra constant, but we know that PDFs integrate to 1. So you have an extra, constraint there. So yes, you can recover the PDF from the score function in 1D. I'll leave it an exercise to you to figure out if that generalizes to a million dimensions. Okay, enough of 1D. Let's move on to 2 dimensions here. So this is a mathematical distribution that is popular in imaging. It's related to what we call the total variation regularizer for for inverse problems in imaging. In 2 dimensions, so this is, think of an image with just 2 pixels, and I'm taking the absolute difference of the values between those 2 pixels. And if I turn that into prior, then I exponentiate it like this, and this is what that joint distribution would look like. And this prior basically is saying neighboring pixels in an image are more likely to be similar than they are to be different. And so that's why the prior is higher along the axis where x1 equals x2. And then the more different the 2 neighboring pixel values are, the lower it is. And that's why the distribution falls off as we go away from that. So this is a 2-dimensional distribution. The score function is the gradient of it. That means the score function is a 2-vector as well. All right, so it has 2 components. The derivative with respect to the first component, the second component, those happen to be these 2 very piecewise uniform functions over here. And so I think in this case, the best way to visualize is take those 2 components and make it as a quiver plot where you draw arrows showing at each point in the distribution, where does the gradient point? Where does the score function point? And it points uphill, right? So if you're at this point over here, the score function is pointing you towards a direction of higher likelihood, right? And higher so over here in the corner, x2 is very different than x1. And the score function is saying, oh, if you want to be a higher probability, it should move in that direction that takes you towards pixel values that are more similar. Again, just trying to give you some intuition about score functions. Okay, so hopefully I've convinced you that maybe score functions, the gradient of the log of a distribution, would be useful to learn for generative modeling. So then now the question is that we'll spend several slides on, given some training data, how do you actually learn that score function? So you've got a model of some sort with some parameters. How do you fit the parameters given a bunch of training data? You don't want to use maximum likelihood because that requires the normalizing constant. You want to fit the score function. So going back almost 20 years now, the first approach that was proposed is what today we would call explicit score matching. So you try to get an estimate of you take your data and do some kind of density estimation to try to get an estimate of the density of the data. Then you take the derivative of that, the gradient of it, the log of that, and that's your data score function. And then you have this model that you're trying to fit to it. And so you say, okay, averaged over all of my training data, give me the score function that best fits that score function of the data. That makes sense. And how do we measure best fit in the literature? By using the 2 norms squared, because that's the one that's tractable. So the problem is the data, when I just give you raw data, it really doesn't have a distribution or a score function, right? We make up a distribution by doing kernel density estimation or something similar, but we don't know the truth. If we did, we would be using that in the first place. And so it's a little bit annoying the way this explicit score matching depends on the data in this way. So the same individual who published this explicit score matching, in that paper, he pointed out that there's another way to do it that we now call implicit score matching. He has some clever derivations involving changes of variables and the like in the appendix of his paper that shows that if you average over the training data, so this is t going from 1 to t, the number of training samples, the partial derivative of the ith component of the score function plus its squared, that minimizing that turns out to be the same as minimizing this. And now you don't need to know the true distribution of the data anymore. So that is called implicit score matching. It's been around almost 20 years, but only really caught on. Well, it doesn't work that well. So that's why it didn't catch on really well initially. All right. And so what's caught on, what's really made this field popular in the last few years is a better approach called denoising score matching. I'll talk about next. So in 2011, so we're getting a little more than 10 years ago now, Vincent showed that explicit score matching and as this is equivalent to this other approach called denoising score matching. So I've just repeated what the explicit score matching formula is at the top, which I told you we didn't want to use. And he showed remarkably that that's equivalent to the following cost function that we can use for fitting the parameters of a score-based model, where basically you, let me try and get this in words. You take your training data and you add some Gaussian noise to that training data. And then you ask your score function plus the amount of noise that you added, suitably normalized by the variance of the noise that you added. You try to minimize that sum. And this has been thought of it by people who came up with it as a kind of denoising operation, because you're adding, let me walk through that again. You're adding some noise to your data. And then you're asking that the score function go in the negative direction of the noise, right? Because you could think of it this minus the negative this, right? So if you remember again, the score function is supposed to point uphill. So if I add some noise, you'd kind of like your score function to go in the negative direction of that to bring you back to the original noiseless data. That's the intuition behind this process. And this turns out to be more stable for fitting score functions than either of the approaches that were proposed about 10 years before that. And mathematically turns out to be equivalent as well. So it's not just an ad hoc thing. It actually is mathematically equivalent. All right. So, but you notice you have to add some noise to your data. And so the actual question is, well, how much noise should I add? And the modern answer to that question is many different noise levels, not just a single noise level. And this was the really secret sauce that was just discovered in the last, let me say, I probably have a citation here. Oh, I do, but without a year. In the last 3 or so years that really made this field take off. Adding a signal, and I've got a Julia code that I've played with this myself. It's really hard to do with a single noise level, whereas if you do a bunch of noise levels, it turns out to be more stable to train, more reliable, and so on. And so now you, instead of coming up with a probability model that just depends on a single, perhaps large parameter vector theta, you come up with what's called a noise conditional score network, because these things are typically implemented. This function here is often implemented as a neural network. So the input to the neural network is your, in my case, image plus some noise, and theta would represent the parameters of the network. And these modern methods have not just the image as an input, but also an additional input somehow into the networks that is the noise level. So you're really training a family of networks at the same time for different noise levels. And there's a recent paper that recommended actually this function could be as simple as just taking a neural network and normalizing it by sigma. It's not clear to me that's the best choice, but that's a recommendation in a recent paper. All right, and for each of the, it turns out in order to do unit balance and empirically, there's various justifications for it. As you try each of these different noise levels, you've got an error here, a denoising level, and you end up doing a weighted combination of these different noise levels, where the weighting turns out to work out well to be the variance of the noise that you added. So interestingly, the higher noise you add, the larger weight you give that in this overall loss function for training. All right, so there it is in equation form. I think I have a picture. Oh, I have some examples here. Yeah, so here's 100 data samples. If I just if I add very, very little noise to them, you just get one spike at each data sample and you get a histogram with 100 points in it. Not very interesting. As I start to add more and more noise to that data, I am getting, well, for those who are familiar with density estimation, these are Parson window density estimates with wider and wider kernels. You start to see something like the shape of the distribution, but as you add more and more noise, eventually it just looks like a Gaussian, right? As if you're adding more and more Gaussian noise. And that is the modern approach to doing noise conditional score matching or training, is you start with your training images and you add more and more noise to it till you get to the point where the original image is essentially gone. You've approached all the way to just a essentially an IID Gaussian noise distribution. And in the process of doing that, you fit a neural network that's modeling your score function. And then once you've done that fitting, when you are ready to draw samples from that distribution, you run this process in reverse. And when I say this process, the modern explanation of this, modern as in 2 years now, which for internet or for machine learning might be ancient, but okay, 2 years ago, is to describe this with stochastic differential equations. So of course, once you implement this, you discretize it, but the way to think about it conceptually is you're adding a continuum of more and more noise to your image to the point that it finally becomes just unrecognizable image just of noise. And the part that's a little baffling to me, because I'm not an expert in stochastic differential equations, is miraculously that process is reversible. So you can start with noise, run it through this reverse time stochastic differential equation, and from that process, generate samples that came from hopefully the distribution that you've trained if you've modeled the score function accurately enough. And so these score-based models these days are often called diffusion models because these stochastic differential equations for adding noise and then taking noise samples and generating interesting samples from it is very analogous to what goes on in the diffusion equation or diffusion processes. I'll pause here for questions again, as long as they're not questions about details of stochastic differential equations. Okay, I'm sure there are people in the room that know more about SDEs than I do. Okay, so these models are really good at generating samples from distributions if you have enough training data. And one nice thing about them, for those of you familiar with GANs or generative adversarial networks, is that no adversarial training is needed here. There's no adversary here. There's no discriminator or whatever. You're just adding noise, training the denoiser to try and undo the noise for different noise levels. And once you've done that, you've learned a score function that you can use in all the ways that I described earlier, such as generating samples to quantify uncertainty and so on. The biggest trade-off is that it's sort of expensive. So you need to discretize, or at least a couple of years ago, you needed to discretize this stochastic differential equation fairly finely. So it was like 1,000 steps of the reverse SDE to generate samples, which is way more work than once you've gone to the trouble of training a GAN, it's very fast to generate samples from a GAN. So because this is the main drawback, you can bet that there are lots of smart people who are working on trying to speed this up. And I said in the abstract, kind of tongue in cheek, that between the time I prepared these slides and by the time I gave this talk, there would be new work that would make some of it obsolete. And sure enough, there's work appearing in the last couple of weeks beyond what I have here of trying to speed up this sample generation process. Okay, so I won't go through the whole list here. Just the high level picture is it's an iterative process to draw samples, just like Markov chain Monte Carlo is an iterative process. People are working on clever methods for accelerating it using everything from wavelets to ODs to whatever bag of tricks you have, you're going to try to apply it to this challenge. I'll just mention one that's near to my heart, which is that I'm really interested in three-dimensional imaging problems and generating these samples in three dimensionals. Like a typical chest CT would be a 512 cubed voxel volume. That's almost 1 billion parameters. And that's not going to be so easy to train a neural network method to generate those samples in a reasonable amount of time. Somebody else across the pond has figured out that, okay, I'll make 2D, instead of trying to model the entire 3D volume, I'll model 2D slices of the volume in what in medicine we call the sagittal, coronal, and axial slices, and put those models together so that I can generate three-dimensional distributions from 2D models that are much easier to train. That's one example of kind of a software engineering such modeling trick to try and speed these things up. Oh, I'll mention one other. So instead of doing the diffusion in the ambient space of whatever your problem is, you can use something like a VAE to find a latent lower dimensional representation and do your diffusion modeling in that latent space. And that's what people now call stable diffusion, and is underlying the technology of this company called Stability AI that is, you can read about, you can use their tools and generate deep fakes and all sorts of stuff with it if you want. All right, so those are a couple examples of things that are people doing to try to speed up this process. And what I want to do with my remaining time then is just focus on applications of it. Well, and then maybe a little bit of my research if there's time. So here are some of the applications in medical imaging. I was supposed to talk about medicine specifically. So image segmentation, labeling, is it tumor and non-tumor and so on. I've already alluded to sparse view CT reconstruction for reducing dose, reducing motion effects. MRI scans are kind of long, slow, and so people move. And so if you can if you have priors for how people move and priors for what people should look like, you can try to put the pieces together and correct for motion. Doing image analysis, denoising, super resolution, lots of medical imaging applications already of this. I'll just show pictures of a few of those. So there's just from this year, transactions on medical imaging paper on doing denoising of MRI images. And I'm not sure how well it's going to show up in the lighting in this room, but they have a ground truth image, a high quality image, and they've synthetically added noise to it to simulate what would happen if you had a lower quality scanner, like a lower field scanner that would be less expensive and therefore more available to lots of places in the world. And then they apply denoising methods to it, and they get images that are pretty good looking. I don't know if you can tell, but I can tell for ARM, they've done a good job of reducing the noise. And then what I think is potentially interesting, remains to be seen how it'll be used by doctors, but they've drawn multiple samples of the posterior here of multiple denoising realizations and shown you then the variance of that, which is kind of an uncertainty map. And so there's, depending on some parameters of their algorithm, the details of a step size parameter, I believe, you can see there are certain structures here that show up brighter. I hope you can see that in these uncertainty maps. Doctors are super busy, and whether radiologists are really going to spend the time to study these uncertainty maps, I don't know, but I think they're at least useful for us researchers in the field to try to get an understanding of what are the areas in these images that our algorithms are having trouble resolving, and how might we improve the methods to reduce that uncertainty. Okay, I mostly work on big scale imaging, but people are also applying this to microscopy images. These are people segmenting nuclei from images of cells. And again, in this work, they're also quantifying uncertainty, and they point out in their paper, this is a very recent paper, that this area here of high uncertainty actually corresponded to something that is misclassified. They know, I guess, that this black blob here is not actually a nuclei, it's something else. And they were pleased to see that area, even though it was kind of segmented by their algorithm, was at the same time showed up as being high uncertainty. So that seems pretty useful if you're trying to do something like automate pathology, slide reading, or some sort of scientific experiment where you just need to know under various experimental conditions how many nuclei have grown or whatever, and you don't want some poor graduate student to have to count these things by hand. And so you get an automation, you use AI to help automate it, but then you also want to know some confidence of your values. All right, and even though I'm not showing you the details, this is based on diffusion-based score models of the kind I've been describing to you. All right, I already talked about that. Okay, I have a few more minutes, right? So I've been extolling the virtues of generative models, but there's also, this is AI, we should also talk about the potential drawbacks. So, and you don't have to hear me, you can go read the New York Times again to hear about the drawbacks. This was the same New York Times article I cited several slides ago about fake faces, pointing out, what's it say here? Then there are odder artifacts that can appear out of nowhere. So if you look at this image for a minute, hopefully you can see there's a bit of, I don't know, ear, skin or something that's appeared up here in the hair. Now this article was from a year or two ago, maybe there are better methods now, but we worry about generative models producing things that are not real. And if you're just making faces for, I don't know, computer games or something, maybe this doesn't matter. But if I'm going to be using this for inference in medical imaging problems, I don't want my generative model to make tumors where they're not, or vice versa. And so I want to talk in the remaining time I have about models that my students and I, or my group members and I, are working on that are hopefully less likely to make massive hallucinations. So let me step back in time a little bit. Generative models have a long history in inverse problems. They go by the name Markov random fields going back decades, even back to the time I was an undergraduate. So that's a really long time ago. And the models at the time were typically built out of collections of pixels they called cliques, and they were typically 2 by 2 or 3 by 3, or maybe a really big one would be 5 by 5 cliques. And you would make up handcrafted, so mathematically designed, not data driven, typically expressions for the probabilities of configurations of the pixels in those cliques. And at least at the time I was reading these papers, they were mostly for inference, although there were some people also using them for generation. There's a paper from '94 where they were empirically saying, what if you did MCMC with these kind of priors? What kind of images would you produce? And in their abstract of the paper, they say these common Markov random fields are not capable of representing the moderate to large scale clustering that's present in natural occurring images. And these are some of the samples that they drew from these distributions designed by Markov random fields using these very small base elements, cliques of pixels. Now, in my scientific applications, I don't need moderate to large scale features because my imaging system already gives that. So in fact, okay, yeah. So in MRI, we collect samples in the two-dimensional Fourier transform space of the slice that we're imaging for 2D MRI. And we have lots of different ways to do that. The simplest way is just collect all the samples get a two-dimensional Cartesian grid and just do an inverse FFT, and 90% of clinical MRI scans are done that way. But if we want to make the scan go faster, we don't collect all the samples. We collect a subset of samples, or we sample in a non-Cartesian way. And these are examples of some of the non-Cartesian sampling trajectories that we use in K-space, in spatial frequency space. And a common property of all of these sampling patterns, both the ones used clinically and the ones used in research, is that they densely sample the center of K-space. This is where the low frequencies are. If you just took the raw data, these are all incomplete. We're missing parts of K-space. But if you just took the data we have, especially the center part of K-space, and did an inverse Fourier transform, you would get a blurry version of what the patient's brain or whatever you were imaging looks like. So it's not the gross, what's the word they use? It's not the moderate to large scale features that we're missing in these inference problems. We're missing the fine details. We have the gross features already in the data that we've collected, but there's sort of gaps out here in the edges of K-space, high frequency details that we're missing. And I believe, it's a conjecture, and we're working on it, and the answer will not appear in the next 5 minutes. I believe that we can probably get that with smaller scale models. We don't need generative models that generate entire heads. If we have generative models that can model patches of images, then that might be good enough for filling in the missing details in this kind of underdetermined inverse problem. And I'm not the first to say there's a lot of patch models that have been used for inverse problems, patch GANs, patch dictionaries, and so on. Curiously, though, a very recent paper in my own field, a survey paper on generative models, didn't mention the word patch once, as if the field has sort of gotten really excited about pictures like this and wants to deal with generative models for whole images. I'm not sure that makes sense. So I'm interested in exploring whether patch-based models could provide better robustness to distribution shifts, reducing the risks of, hallucinating a tumor that's not there or whatever, because I'm not going to generate pictures are not going to generate structures at the size of a whole tumor, but rather just groups of pixels. I think this is especially important for applications where we have very limited training data, right? To train the models for some of the applications I showed you, they use a lot of data, thousands and thousands of images. In dynamic imaging, especially dynamic MRI, we can never really get a single fully sampled data set to train on. In dynamic MRI, the patient is changing as we're imaging, and so it's always undersampled. So we always have limited training data. But I still wonder, could we use something more modern than Markov random fields, the latest score-based models for patches? So how might we do that? So this is the research part now. Is going back to sort of the mathematical framework of Markov random fields, which people in computer vision also call a field of experts model, where you write down a joint distribution. This is a prior for the image that is a product of individual terms for individual patches. So the idea, it's also called a product of experts. They're very closely related. The idea is you have a bunch of critics, I guess, looking at an image, but each one of them is only looking at a small patch of the image. And if any one of those critics says, oh, that patch is really unlikely, this must be a bad image, then you give the overall image a low probability, right? Because when you multiply a bunch of exponentials together, any of those that are really small will drive the over probability lower. So wording it positively, the most likely images are those where every patch in the image is a likely patch according to your prior distribution that you need to learn from training data. Okay, so that's the idea of Markov random fields or field of experts models. So that's the parametric form. And these things in the exponents here are called clique potentials. All right, so I'm going to assume that my images are sort of shift invariant. So my clique potentials are all come from a parent clique. I take my image, I grab the Cth patch from that image, and I put it in this parent clique function, and that's a sort of shift invariance model. And when I put that shift invariance assumption into this model and take the log, I get this expression right here. And then when I take the gradient, I get the score function. So the overall image score function turns out just to be some sort of assembled from pieces of a kind of parent score function that is a score function for individual patches. So instead of learning a score function for the whole image, so I learn a score function for patches, and then I have a concrete way of assembling that to get a score function for the whole image. But really, I'm learning statistics at a patch scale. And so if my patch is 3 by 3, this score function is a function that takes 9 inputs and produces 9 outputs. That can be done with a multi-layer perceptron. I don't need a giant network necessarily to learn that score function at that scale. I don't expect to be able to generate beautiful brains from this in isolation, but I hope that by combining them with some data from an MRI or CT scanner, I can make nice brains. And so once I have that as my thing that I need to learn, I need to learn the patches, the score function for patches. I'm going to use denoising score matching again, but now by taking patches from training images, and I don't need a lot of training images. Even one image has a lot of patches in it. So give me a half a dozen images, and there's a lot of patches that I can make this capital T in the sum very large, add noise to each patch, and train a score function at the patch level. And how am I doing here? A couple more minutes. Yeah, all right. Yeah.
You have until 4:15.
Okay, I don't need to rush even. Any questions so far? Oh, it's there. Let's see here. Where did it go? So the partition function. So I'm assuming all my partition functions are shifted versions of the common partition function. Okay, that's the V without the subscript. Okay, and its gradient is the patch score function. So maybe you're asking a good question. At the end of the day, I will not have learned the partition function. I will have learned its gradient. All right, and then it's an integration question if you really want to get back the original partition. Oh, I'm sorry. You said partition function. You didn't ask about the clique potential. Maybe you weren't here earlier when I pointed out. Okay, so when you take, I think you're a statistician, and I said earlier, maybe before you were here, that statisticians, the gradient is respect to the parameter theta. In the computer vision literature, the gradient is respect to x. And so once I take the gradient respect to x, the partition function as a constant disappears. Maybe that answers your question. So when we learn these score functions, we're learning the gradient of the log prior with respect, the gradient with respect to x, not theta. Did that answer your question? I need to learn theta from training data. Okay, that's what the score matching process is doing, right? What's that? Well, when I'm done, I will not plug this theta hat back into Z because I don't know Z even, right? I'm going to just use that score function for all inference afterwards. Okay, I will never get the score function. And so I will never do, so I won't really do map estimation. Oh, no, let me see here. Yeah, anyway, anything that requires the partition function, I won't be able to do it. Not just me, anybody using these score-based models will not be able to do.
Once you've integrated the score function.
Which you don't usually do, though.
Well, at
Okay.
the end of the day, in terms of recovering stuff, you can recover the. That's already established.
I mean, yes, but I'm dealing with almost 1 billion parameters, right? So I can't do the billion dimensional integral, right? So in principle, I can write it down. I wrote integral of x, but that was a bold x, dx, right? That was a bold x as a vector x in a dimension. So here I could do the integral if I'm only doing like 5 by 5 patches. That's still a 25 dimensional integral. I mean, I'm not going to do it. So people in this field are just learning the score function and then using that period. Let's see here. Yeah, what's that?
From noise.
Mm-hmm.
Where is it generated for patch, or is it
So I'm not so interested in generating. I'm not going to show you any. I don't think I'm going to show you any generative examples, right? So I'm going to only use this for Bayesian inference, and so I will be using this expression right here that expresses the gradient of log prior in terms of the gradients of all the patches and adding those all up, and I'll be using that in my stochastic gradient descent. But I won't be, but stochastic gradient stat combined with the gradient of the log likelihood so that I can do, basically kind of, Bayesian estimation. I would not claim this is going to generate anything better, might not generate anything better than these kinds of pictures. Right? Well, I'm using a little bit larger patches possibly. Okay, so this is really, I gave this part of a talk at a conference just a few weeks ago. And my graduate student, Jason, gave me the results like while I was at the conference. And I haven't gotten any updated results from him. So these are the ones from a couple of weeks ago. And so this is an example where we just used 3 by 3 patches. And I had lots of, too many, 1,000 training images that I call this the pizza phantom. Every one of these images looks like this. It's a disk, slightly different position with random disks located within it. And even though it's only a 3x3 patch, he learned a pretty deep multi-layer perceptron model of 9 inputs and 9 outputs, right? 3x3, there's 9 pixels there. I don't know, you may have heard the expression graduate student descent, right? Some optimization process graduate students do. I have no idea how he chose this number of layers. And this collection of activation functions, this is very preliminary work. All right, so here's a clean image, here's a noisy image. And so now I can, let me see, this is the, in fact, in this case, we're trying to do map estimation here, but we're doing it just by gradient descent. So we're not doing Langevin dynamics here. We're starting with an initial guess. In fact, our initial guess is the noisy image itself. And then we just apply gradient descent using that score function, which involves the score functions of each patch, like you were asking about, added up, along with the gradient of the log likelihood. And this is the denoising problem. So that is just y minus x or x minus y, well, over sigma squared. For those who are used to regularization, like I am, in problems with a regularizer, like even Tikhonov regularization, there's a beta parameter, a regularization parameter, lambda, beta, alpha, whatever, that you need to manually tune. The interesting thing here is there's nothing to manually tune. Once you've learned this score function, that's supposed to be the gradient of the log prior for this image, and so you don't need to tune anything. So there is no beta in this expression. There's just the log likelihood and the log prior. Let me see here. And so then we denoised, let me show it again here. We took this noisy image with this PSNR and applied BM3, block matching 3D, which is a kind of state-of-the-art pre-neural networks denoising method. Jumped up to 34 dB. We used total variation regularizer, only got 33 dB. And then we used the score matching and we got 36 dB. All right, so that's an anecdote, one example. Now I'm not super happy. I mean, I know that these images are circles. And if you look at some of the shapes here, they're kind of blobby. But keep in mind, my prior is really working at a 3x3 patch level. So you can't really tell the shape of a circle. And in a way, that's partly the point of working at patch levels. And this is, oops, sorry, this is a very noisy image. Looking back here, I know that's a circle, but if I just showed you this image, you might be hard pressed to know that's a circle. In fact, you might even miss, if I didn't show you the ground truth up here, I don't know what it looks like up there, you might even miss the fact there's a circle right here. So I'm kind of glad that all of these algorithms at least got something here, but to my eyes, if I want to look at it with rose-colored glasses, maybe it jumps out the best in this one, but this is just one anecdote. Now, one of the things my long-term interest here is making these methods generalizable to distribution shifts. So here are the results I just showed you, and here are results that I changed ever so slightly, and you'll notice this score matching approach suddenly worked a lot worse. Can anybody see what I changed? You might not be able to see it from the back of the room. Yes, exactly. So all I did is I took the image and multiplied it by 2. All right, and with the total variation regularizer, as long as you adjust the regularization parameter proportionally, it works exactly the same as before. But this score matching model was trained on a whole lot of images that looked like this with ranges from 0 to 1. And so you throw out an image with data that suddenly goes from 0 to 2, and it works a lot worse than before. And this is not great. Now, there's ad hoc ways that you could normalize your data to try to make it so it's all in the same range as your training data. But if something as simple as a scale factor is a distribution shift that throws the model, okay, I can shift that with normalization, but what other invariances have I lost that I'd like to in the future figure out how to try to build into this? I'm going to skip that. In fact, I think in the interest of time, we've played with rectangles as well. I will skip that. I think I'll skip the rest of this and just skip the summary here. All right, so hopefully, if you hadn't seen it before, you've now got some insight into about learning score-based models. And you can do this with a score matching process, either for whole images if you have enough training data, or with patches if you have limited training data, like we're working on. I'm trying to think about various kinds of invariances. I would like invariance to shift, to scale, maybe to left, right flips, rotation, whatever. I'd like to get all of those invariances built into the fitting process inherent in the model without just doing brute force data augmentation, which we could do, but hopefully try to make it more integrated. we need to do a lot more comparisons of whole image models versus patch-based models. Again, not for generating graphics for computer, games or whatever, but for these scientific inverse problems. There's recent work on what's called multi-scale score models. And in some sense, my patch model is just the finest scale. So maybe I could have a couple scales with still not trying to generate the entire image. More trade-offs to explore, and really work on this in dynamic imaging problems where my data is really 3D plus time, and I'll never have enough training data to train a whole image model from it. So if you're interested in playing around with this, with a simple example, there's a Julia repo I have that generated actually many of the plots shown in this talk. So thank you very much for your attention. Happy to take more questions.
Yeah, questions from the audience?
There's one
Yeah,
way
the
in the back.
top.
30 what? Page 34. Yes.
If I care about image reconstruction task, would you just replace the log likelihood?
Yes, that's right. So here we're just doing denoising, but ultimately we will put the log likelihood, the gradient to the log likelihood that goes with the whatever your image reconstruction problem is. And I think we'll eventually do it with the Langevin dynamics so that we can do samples from the posterior instead of just doing greedy gradient descent. We're very likely getting stuck in bad local maxima when we just do this greedy version. So the stochastic version, it has two benefits. You get the sort of uncertainty estimates, and you get an ensemble that you could take the mean of, for example, and probably be more robust, less likely to be just stuck in some bad local minima.
Yeah, would you think it beneficial to use score-based model in other optimization algorithms?
I didn't catch that. You said, would it be beneficial to what?
To incorporate into different optimization algorithms.
That's an interesting question. So the question is, would it be useful to incorporate score-based models into other optimization algorithms? So all we really have is the gradient. So I guess as long as it's a gradient-based optimization algorithm, we have a model for that gradient. You can plug it in. Let me see here. But I need to caution you. Let me see. In some backup slides, I took some training images and I estimated the joint distributions of pairs of neighboring pixels from those training images. And then the derivatives of that are the score function. So I'll just say it in words. These problems are, I think, very non-convex. My log likelihoods for most of the imaging systems I care about are reasonably well behaved. So that part is okay, often convex. But the score functions for images that we're often using for training here, they're pretty non-convex. So I think that is another reason. Okay, I shouldn't say the score function is the log priors are non-convex. And so I have a feeling we really do want to be using stochastic gradient descent. Maybe an accelerated version or something, but stochastic gradient descent, because I think if you don't do it stochastically, any other optimization algorithm that's sort of greedy but not stochastic, I think you're very likely to get stuck in strange local maxima. I'm just giving my intuition as answer, no theorem. Okay, it's a good question.
So you're talking about denoising score matching, right?
Right.
And so the model for the denoising, I mean, do you actually assume a simple Gaussian model when the problem is being solved, or have you or have others actually tried looking at more suitable noise model, especially in the medical imaging? I mean,
Excellent question. So I'm really glad you asked that, because I've even had debates with my own group about this. So this score matching process, I've interpreted as learning a denoiser, and the mathematical equivalence that was shown by Vincent is specifically for Gaussian noise. He's usually that the derivation is very similar to the derivation of Stein's unbiased risk estimate, if you're familiar with that. And that also has been designed for Gaussian noise. But once it's learned, it's a model for the log prior. And you can combine that with a log likelihood that goes with any imaging system you want. I've got students who are working on SPECT imaging that has Poisson noise, and we're using the Poisson part there. Okay, but this is still just a model for the prior. It has nothing to do with the statistics of the imaging system that we might use for sensing later.
And it works well.
And I'd say that's work in progress. I mean, but if it doesn't work well, the problem's not the Poisson part, it's that we're still figuring out how to model the prior
Okay.
correctly, right? So, so I don't think there needs to be any correlation between the Gaussian noise that's used here just for learning the prior. In fact, one thing I didn't say is once you've learned this prior, well, in fact, actually, let me go back to this picture here. Once you've learned this prior, you're taking the high noise level and you're running for drawing samples, you're running the reverse CD, and you're going back almost all the way to the point you've almost added no noise. And so the noise distribution sort of became irrelevant that, right? That's just having to do with modeling the prior. It has nothing to do with the whatever kind of sensor noise you might have in the inverse problem later or inference problem more generally later. I'm really glad you asked that because I think that's a subtle point that gets missed here. We're not just training a black box denoiser, we're training a score model that we can then use for lots of things, including denoising as well as other inference problems.
Thank you.